A surprising number of high-energy stream sites with visible plunge pools are walked past every year by hikers, campers, and even amateur rockhounds without a single pan dipped. The reason? Most assume that the waterfall itself, with its turbulence and froth, is too chaotic to trap anything valuable. But that very turbulence, when followed downstream a short distance, becomes the first natural sluice. Just beyond the chaos, water slows and heavy particles settle. Miss that transition zone, and you miss where nature does your concentrating for free. Unlike the uniform flow of a calm stream, waterfalls create sudden changes in hydraulic energy. These drops force lighter material to stay suspended longer while heavier materials, gold, platinum group metals, diamonds, and dense oxides, slam into bedrock or fall into crevices beneath the current. In many cases, these concentrations don't settle right beneath the waterfall, but accumulate in low-pressure eddies 3 to 10 meters downstream. The optimal zone is often just where the foaming water clears and begins to flatten, where a miner's eye sees not beauty but opportunity. Field tests confirm this repeatedly. In British Columbia, a narrow waterfall on serpentinized terrain produced no color in the pool itself, but 10 meters downstream, coarse black sand layered with garnet and flecks of native gold turned up in every third pan. In Brazil's Chapada Diamantina, certain diamond-bearing rivers show similar behavior. Diamonds rarely settle in the roiling plunge zone. They are found where turbulence dissipates and bottom textures allow them to lodge. This has practical implications. Rather than sampling in the obvious froth or basin, concentrate first on downstream shelf zones, especially where bedrock is exposed or where sandbars end abruptly. Look for areas where fine gravels are trapped behind protruding rock or root mats. These are miniature sluice boxes built by nature. Even a single heavy mineral grain in this zone, if it fluoresces or reads dense, can indicate upstream potential. At first glance, all waterfalls might appear equal scenic, loud, and wet. But beneath that visual spectacle is a geological filter. Some waterfalls, even with dramatic vertical drops, are practically barren in terms of mineral accumulation. Others, with modest height but key bedrock features, quietly trap decades of gold finds or diamond indicators just beneath their surface. Knowing the difference means not wasting days on false hopes. 3 traits separate mineral-rich falls from the rest: bedrock composition, plunge pool geometry, and sediment interface. First, consider the substrate. Waterfalls anchored in hard, erosion-resistant rock like quartzite, serpentinized ultramafics, or basalt tend to hold deeper crevices and longer-lasting traps. In contrast, waterfalls carved into soft sandstone or friable schist often shed their pockets too quickly for minerals to accumulate. A fallen gneissic terrain may look ideal, but if the foliation planes run parallel to flow, heavies slip right past. Second, shape matters. A fall with a broad, shallow plunge pool may look ideal for swimming but won't do much to slow and separate dense material. The best falls for mineral trapping have a narrow outflow channel that forces water to compress, lose energy suddenly, and drop its load. A horseshoe-shaped or pocketed plunge zone with downstream constriction creates exactly this effect. Think of it as a natural riffle system. If the water has to turn, twist, or push through bottlenecks, the odds of heavy deposition rise. Third, what lies beneath the visible pool tells the real story. Look where gravel meets rock, where silt gives way to coarse sand, or where black layers streak through brown. These interfaces often contain years of seasonal deposits. If there's moss growing right up to the waterline on exposed rock, you may be looking at a stable shelf, a prime test spot. A crevice tool and a short pry bar can open windows into these packed layers. Watch especially for streaks of ilmenite or chromite, which appear as dense, black metallic bands when dried. Don't overlook sediment grain size. In promising falls, you'll often find a sharp transition between fine silt and coarse sand, evidence of differential settling. Where garnet grains or angular quartz pebbles are intermixed with magnetite or hematite flakes, it's worth sampling. A quick pan in these zones can tell you in minutes whether to proceed or pivot. But knowing the structure is only half the game. The movement of water, its speed, force, and direction, turns that structure into either a trap or a flush. Understanding how velocity interacts with terrain is the next step toward deciding whether your waterfall is a keeper or just a scenic diversion. The key to whether a waterfall becomes a mineral concentrator isn't just what lies beneath, it's how the water moves over, through, and beyond it. Nature's hydraulics do most of the sorting work a prospector would otherwise perform by hand. But to read it properly, you must think like water. Not just where it falls, but where it slows, curls, and drops. As water approaches a fall, its speed depends on both slope and channel constriction. A narrowing upstream often accelerates flow just before the edge, which in turn affects how and where material launches. A wide, gentle approach tends to spread sediment out. A tight, steep chute focuses it. Water doesn't just pour over, it jets. This jet creates what's known as a plunge velocity, a downward force that hits the pool floor with significant energy, often enough to scour loose material from even compacted sediment layers. But here's the twist: what gets flushed depends on density and particle shape. While light material remains suspended in the turbulence, dense particles behave differently. Gold, with a specific gravity around 19.3 and diamonds near 3.5, tend to arc downward and drop quickly if flow energy allows. Their momentum is largely vertical. What happens next depends on the shape of the receiving pool and the downstream gradient. If the plunge pool is deep, with a flat bedrock floor or catch basins, these dense grains may lodge almost immediately. But more often the water rebounds upward and spins outward, forming circular back currents called eddies. It's in these reverse spirals, especially on the inner arc of downstream bends, that gravity overcomes velocity. The physics are nearly identical to artificial sluice designs: sudden drop, directional turbulence, and low-pressure eddy zones. From a practical standpoint, this means you should examine not just the base of the fall, but 5 to 15 meters beyond it. Walk the inside curve of any downstream meander. Use your foot or a small spade to peel back the top layer of light gravel. If the underlying zone is compact, dark, and slightly greasy to the touch, you're looking at a natural heavy mineral mat. These mats often trap gold fines, chromite nodules, and in rare conditions, rough diamond crystals transported by lamproitic or kimberlitic float. Look also for small scallop depressions in the rock just below the waterline. These often act like mini riffles, catching and holding heavies after rain events. When dry or at low water, these spots yield some of the clearest signals. If black sands layer neatly or if garnet-rich gravel is visible in distinct pockets, it's time to test. The velocity logic also explains why two waterfalls just a few kilometers apart can yield drastically different results. A narrow chute with a sharp vertical drop and immediate downstream constriction will concentrate values. A wide fan-shaped fall with no downstream bottleneck will disperse them. Recognizing these dynamics without even panning can save hours or days. Yet even with ideal water behavior and structure, there's still the matter of signal. How do you know when black sand is just black sand and not something more? That starts with recognizing specific mineral indicators underfoot. Not all black sand is equal, and nowhere is that more obvious than in the chaotic environment of a plunge pool. The key lies in how the heaviest particles behave as energy dissipates. While tourists marvel at the falling water, a trained eye reads the eddies, shelves, and crevices below like pages in a ledger. These formations track the passage of floods, droughts, and mineral loads over time. At the point of impact, water carves downward into bedrock if it's soft enough. This erosion creates pockets and ledges where dense materials settle, especially just after major storm surges when energy peaks. Look closely at the concave depressions on either side of the main impact zone. They often host spirals of compacted sediment with a granular metallic sheen when dried. That's your first hint. From there, the water rolls outward and upward, forming an outer rim known as a back eddy zone. It's in these arcs, especially along the inside curves of downstream channels, that the most reliable concentrations occur. Black sand isn't diagnostic by itself, but its layering tells a story. Thin, consistent bands suggest annual deposit cycles. Thicker, clumpy mats mixed with angular quartz and garnet grains imply rapid loading events, often associated with flood gold. Field identification here relies on touch and texture as much as sight. True heavies resist your fingers. They don't scatter like ordinary sand. Run a magnet through a handful and separate the responsive magnetite ilmenite from the inert gold garnet chromite. If the residue is mostly magnetic, chances are you're dealing with a high iron deposit. But if any remains unmoved, examine it under a loupe. Platyfish gold will reflect in flat flashes. Garnet and chromite appear as rounded or subangular grains, often blood red or jet black under light. In one verified case from the eastern Sierra Nevada, a team found gold fines averaging 72% purity compacted into a ledge behind a submerged boulder less than 5 meters from a waterfall base. The signal was invisible at first, just dark gravel under slow water. Only after sieving the top layer and examining the concentrate did the telltale flakes emerge, clinging beneath dense magnetite. The density contrast was the giveaway. Gold doesn't move even in flow that scatters everything else. Another overlooked indicator, surface polish. Gold grains rounded by travel tend to settle near outer arcs. Angular gold, fresh from a nearby lode, often hugs the inner zones or gets trapped in root mats where no one pans. Diamond indicators behave similarly, though they tend to move farther before settling due to their lower density. When garnet, chromite, and ilmenite appear together, especially in roughly equal proportions, it's time to consider deeper potential. Before the first drop of water ever touches your pan, the terrain has already given up its first secrets, if you know how to read them. Many miss this step entirely, rushing into panning only to find hours wasted on magnetite-rich gold-poor sand. Yet just standing at the edge of the fall, a trained eye can spot half a dozen signs pointing to whether the site holds potential, or is best left undisturbed. Start with staining. Oxidation patterns on exposed rocks above and around the fall often signal mineral-rich water upstream. Look for rusty orange to deep brown streaks on boulders, especially near fractures or seeps. This gossan-like weathering frequently accompanies sulfide mineralization, a potential indicator of gold-bearing veins. But beware, iron staining without supporting clues often leads to pyrite-rich zones devoid of native gold. Next, examine any exposed gravel bars or silt shelves along the plunge pool perimeter. Scan for tiny flashes, ruby red garnet grains, opaque black chromite nodules, and submetallic ilmenite flakes. These aren't valuables themselves, but they're key components of what geologists call the heavy mineral suite. Their presence in natural concentration suggests sustained hydraulic sorting. If you see all three, particularly in a confined pocket or swirl zone, you're likely within reach of a natural trap site. Don't overlook texture underfoot. Walk the banks in dry season or low water and press the sediment with your boot. Material with a greasy or compacted feel, especially if it contains tiny angular quartz grains mixed with black sand, is often a long-settled pay layer. In contrast, fluffy or loosely bound gravels tend to be recent wash and rarely hold much. Then there's plant life. Aquatic moss growing in tight mats over submerged rock shelves often traps finds, especially gold and platinum group elements. These organic mats act like natural miner's moss, catching microflakes in their filaments. Carefully lifting and rinsing a patch in a pan can yield surprising results, gold specks clinging where none were visible in the surrounding gravel. Field optics matter too. A simple 10x loop can immediately separate false positives from genuine clues. Examine the grain faces. True gold will deform slightly under pressure, while mica will flake and reflect in rainbow hues. Garnet grains will be deep red to violet under light, often semi-translucent. Chromite is matte black, and its spherical or nodular shape makes it easy to identify once wet. Finally, altitude and accessibility tell a longer story. Waterfalls above 1,000 meters in ultramafic or metamorphic zones tend to yield more indicator minerals per pan than those on sedimentary terrain. Remote doesn't always mean rich, but easy-to-reach falls with obvious paths have often been overpicked. Prioritize sites with less foot traffic and evidence of seasonal sediment layering. If a spot looks scoured but shows embedded black sand in rock crevices, it's a candidate. Long before water ever touches your sample, a simple dry scan with a magnet and a hand lens can eliminate 80% of false positives. This first-pass technique, overlooked by most beginners, lets you read the mineral story embedded in sand and silt without ever filling a pan. And it's especially effective at waterfall sites, where the energy of flow has already performed a crude pre-sort for you. Begin with a small scoop of the heaviest-looking sediment from a crevice, bedrock depression, or black sand pocket just downstream of the fall. Let it dry in your hand or on a flat rock. Once it's no longer damp, sprinkle a thin layer onto a white plastic tray or sheet of paper. Then hover a strong neodymium magnet just above the surface. Watch what jumps. If the bulk of the sample leaps toward the magnet or forms chains, you're looking at magnetite or less commonly ilmenite. Both are dense, black, and common in heavy mineral zones, but they're not worth chasing unless paired with other indicators. If the response is strong but uniform, you may be in a magnetite-rich but gold-poor system. In contrast, a sample that shows patchy or partial magnetic response often holds a mix of minerals, including non-magnetic heavies like chromite, garnet, and possibly gold. Set aside the non-magnetic portion and examine it under a 10x loop. You're looking for three main features: shape, luster, and color. Gold grains will appear soft-edged, often flattened with a buttery metallic sheen that doesn't glitter, it glows. Unlike mica or biotite, which flash in multiple colors, gold reflects a consistent tone from any angle. Garnets will appear rounded, often reddish or purplish, and translucent at their edges. Chromite shows up as dense, jet-black nodules with a dull or slightly resinous luster. The real skill lies in spotting composite particles. For instance, a dark grain with a slight metallic edge may be a gold ilmenite intergrowth, something that forms when both precipitate under high-pressure conditions upstream. These rare finds signal proximity to a source deposit and are worth documenting carefully. Note their shape and weight in hand. They often feel heavier than they look. If you find translucent grains with a diamond-like luster, don't jump to conclusions. Many times these are zircon, a common diamond simulant in stream sediments. A loop may show crystal faces or striations, but only later tests will confirm. Still, finding zircon suggests an upstream igneous source, which in turn raises the odds of other high-density indicators nearby. Importantly, this dry test also reveals whether further sampling is warranted. A pocket full of responsive magnetite with no visible non-magnetic heavies usually means the trap has been flushed or never had richer material to begin with. But even a few garnet grains mixed into the non-magnetic residue, or a faint gold glint under magnification, shifts the odds in your favor. The dry scan is your gatekeeper. If it passes, wet panning becomes worth the effort, but don't skip it. Too many spend hours knee-deep in cold water when a 5-minute magnet scan could have saved the day. And once you do move to the pan, what you find or don't in the swirl may force you to recheck your assumptions. Especially when the water gives you a glittering lie. It's one of the most deceptive signals in the field. Dense black sediment layering, high magnetic response, even the occasional metallic flash, and yet no gold, no diamonds, no sail. Plunge pools, by their nature, are perfect collectors of heavy minerals, but not all heavy minerals are valuable. And when magnetite dominates, it creates the illusion of richness that dissolves under scrutiny. This false positive scenario plays out more often than many admit. A prospector arrives at a promising fall, bedrock exposure, strong downstream eddies, even visible layering in the gravel. A quick pan reveals dark concentrate and the excitement builds. But what's actually happening is overconcentration of low-value ferromagnetic minerals. Magnetite, ilmenite, and hematite all share key traits: high density, dark color, and stability in flow. They settle early, trap easily, and form thick mats, but they carry no intrinsic value in raw form. The trap tightens when mica or biotite enters the mix. These flaky minerals reflect light in glittering flashes, fooling even experienced eyes into thinking they've spotted fine gold. But mica floats on water, spreads thin when rubbed, and breaks under pressure. Gold, by contrast, smears but doesn't shatter. A quick fingernail test, pressing a speck against a flat rock, can expose the truth in seconds. If it vanishes under pressure or fans out into rainbow sheen, it's mica. Real gold holds its mass. Even garnet and zircon, both common in high-energy stream deposits, can mislead. Their bright luster and high specific gravity make them seem promising, but they lack the softness, conductivity, or market pull of true gem or precious metal content. Worse, some of these minerals occur in such abundance that they dominate concentrates entirely, crowding out rarer signals like platinum flakes or raw diamond. To avoid the plunge pool trap, move beyond visual confirmation. After the dry scan, try a tap pan test. Fill your pan with local concentrate, submerge it, and tap it gently while tilted. True gold migrates to the corner quickly and stays compact. Magnetite and garnet will swirl and bounce longer. Observe the settling behavior. Inertial drag sorts particles by both density and shape. If everything moves the same, your concentrate lacks high-density outliers, meaning no gold, no diamond, no PGEs. Another safeguard is water displacement. Take a small glass vial, fill it halfway with water, and drop in a single grain from your pan, especially any bright or dense appearing piece. Gold and platinum will sink instantly. Mica, biotite, and even some zircon grains hesitate or flutter down. It's a simple gravity test with immediate feedback. Importantly, not all plunge pool false positives are worthless geologically. The presence of ilmenite, chromite, and garnet in thick concentration can still signal a kimberlitic or ultramafic source upstream, especially if found with trace amounts of spinel or peridot. But without finer discrimination, these signs lead many astray. The next move is critical. After false positives are ruled out and a site still shows potential, you escalate to a full wet pan test, targeting the zones just beyond the pool where flow energy slows and minerals sort by density, not just momentum. That's where the first real hit often happens. And knowing what to look for in that pan makes all the difference. A true hit, in sluicing terms, meets criteria that go beyond shine. Start with volume reduction. After scooping from a targeted crevice or eddy zone, pan down to the last teaspoon of heavy fraction. What you're left with, ideally fewer than 30 grains, should represent the densest slice of the sediment column. The texture should feel gritty and sticky when rubbed between fingers, not powdery or slick. If the entire remainder jumps to a magnet, walk away. It's just iron oxides. But if anything resists the pull, that's your signal to look closer. Gold fines settle quickly and hug the pan rim, often appearing as flattened flecks, irregular micropellets, or even tiny wires. Their softness is key. Tap the pan gently, true gold doesn't bounce. Try dragging a pin across the flake, gold will smear, not shatter. Mica, by contrast, breaks apart or slips away. Diamond indicators behave differently. They don't flash, they persist. Garnet grains, especially pyrope or almandine, appear as wine-red spheres with dull luster. Chromite sits matte and black, often nodular. Ilmenite shows a greasy or metallic sheen. The presence of at least two of these in a single pan, particularly in a stable ratio, boosts the odds that heavier diamond-bearing gravel may exist upstream. False indicators can mimic this spread. Zircon, often misread as microdiamond, will appear bright and angular, but it lacks the hardness and refractive behavior of true diamond, which you can't detect at the pan stage, but you can prepare for. If your concentrate includes garnet, chromite, ilmenite, and trace spinel in a confined area, it's time to grid and resample systematically. Quantify your pan. 1 flake of gold per pan in a high-energy zone is not a hit, but 3 to 5 flakes in successive pans, each weighing 0.01 grams or more is. This is your repeatability threshold. Likewise, if your non-magnetic residue consistently yields translucent garnets and visible chromite nodules across a stretch of 5 meters, mark the zone. Another field trick is density biasing. Fill the pan with the same sediment twice, but once remove all visible magnetic material beforehand using a strong magnet. If your final concentrate increases in visible non-magnetic heavies after this pre-cleaning, you're dealing with meaningful density separation, a real trap zone. In diamond prospecting, few things matter more than context, and no context is more telling than the suite of heavy minerals found alongside each other in stream sediments. While gold gives itself away in color and softness, diamond hides behind a screen of proxies. The key is recognizing the specific quartet of minerals that nearly always precedes discovery: pyrope, garnet, chromite, ilmenite, and sometimes magnesium-rich spinel. Each mineral in this indicator suite forms under specific pressure-temperature conditions common to kimberlite and lamproite pipes, the primary carriers of diamonds to the Earth's surface. They don't originate in streams. They're dragged upward from the mantle, locked in host rock, and liberated over geologic time by erosion. When you find more than one of these minerals together, especially within a confined drainage, the probability of a nearby diamondiferous source increases sharply. Begin with pyrope garnet. Unlike the more common almandine, which is deep red and often rounded, pyrope tends toward purplish red, sometimes even pinkish under sunlight. It has a high chromium content, which gives it a distinct inner glow. Under magnification, it appears translucent with smooth, well-defined crystal faces. In stream beds, it resists transport erosion longer than other garnets, so angularity can suggest proximity to source. Next, chromite. True chromite is jet black with a resinous to submetallic luster and a specific gravity around 4.54.8. In field conditions, it often appears as small nodular or angular grains, frequently mixed into the heavier bottom layer of a pan. Unlike magnetite, chromite is only weakly magnetic. Hovering a neodymium magnet just above a dry sample will cause chromite to nudge, but not jump. This subtle behavior helps differentiate it from stronger magnetic imposters. Ilmenite is perhaps the most deceptive of the suite. It often looks like magnetite, dark metallic, but with a subtle bronze or bluish tint when freshly fractured. Ilmenite is strongly magnetic but slightly less responsive than pure magnetite. More importantly, it commonly occurs in oxidized form, which gives it a greasy or dull exterior. When crushed, it yields a black streak, whereas hematite gives a reddish streak, another simple field test. Finally, spinel, especially chrome spinel or picotite, can appear in highly diamondiferous terrains. It shows up as tiny, deep black grains with strong luster and sharp edges. In panning, spinel is often mistaken for chromite, but spinel tends to occur as euhedral crystals or in fractured shards. It's the least common of the four, but a valuable corroborating clue. What matters most isn't just finding one of these, but the co-occurrence. A stream bed that yields chromite and ilmenite is interesting. Add pyrope garnet and the calculus changes. A cluster of all four, even in trace amounts, signals the need for grid sampling and float tracing. You're likely dealing with glacial or fluvial dispersion from a weathered kimberlite source. Field confirmation of these indicators often triggers a more rigorous test protocol, including sieving by mesh size, typically 0.5 min up, density separation, and heavy liquid tests, though these go beyond what most field setups can support. Still, the presence of this suite means it's time to think not just about the current stream, but the terrain it drains. If gold is present in a waterfall system, it doesn't settle all in one place. It sorts itself by weight, shape, and energy, leaving behind a gradient you can read like a map. Nuggets don't land where specks do. And understanding this pattern can be the difference between walking away empty-handed or hitting the pay layer, just a few steps further downstream. The largest pieces, nuggets, coarse flakes, even wire gold drop first. They settle quickly, usually within the first few meters below a high-energy drop, often in bedrock cracks under root systems or behind heavy boulders that deflect water. This zone is where gravity wins immediately after turbulence fades. It's also where careless hunters waste hours panning exposed gravel while the real prize lies an inch below the surface, lodged in crevices hardened by time. Move 10 meters downstream and the story changes. Here you'll find medium-grade flakes, heavier than sand, lighter than rocks, collected in folds of moss under flat rocks or trapped between compacted gravel layers. This is where flour gold begins to appear, microscopic specks that float easily in water but eventually settle into thin, stubborn layers just above bedrock. It takes patience to find, but its consistency often outpaces the flashier upstream zones in yield. Vegetation offers subtle clues. Moss growing tightly across rocks that are just below water level acts like natural miner's carpet. In high-gradient streams with gold potential, the best finds often concentrate in these fibrous mats. Pull one, rinse it in your pan, and watch what remains. Gold trapped here is almost always flat and bright, easy to miss, but hard to dislodge without intentional effort. Curves and constrictions play a major role. The inside arc of a sharp downstream bend slows water dramatically, encouraging even the finest gold to drop. These inside bends are prime targets for testing. Flat gold behaves differently from rounded sand. It drifts slowly, clings to surfaces, and sinks deeper when current energy fades. A proper tap test during panning often reveals it as a quiet glow at the edge, resisting the swirl. The visual markers that guide you, layered black sands, reddish garnet specks, or orange-stained rock, only tell part of the story. What matters is repeatability. If every third pan along a 10-meter section holds visible finds, you found the gradient sweet spot. That means the waterfall did its job upstream, and nature's sluice continues down here, sorting by weight, letting you read value by location. Most people searching waterfalls for treasure fixate on metals, gold, platinum, even the rare promise of diamonds. But some of the most surprising finds in high-energy stream zones come not from weight, but from the host rocks themselves. Jade and opal, two minerals with wildly different origins, can appear where few expect them, near or downstream from waterfalls, and their clues begin long before the water falls. Take jade, specifically nephrite, which often forms in serpentinized zones where tectonic plates once collided. These rocks, dark green, fibrous, often slippery underfoot, signal deep alteration over time. If you find a waterfall cutting through such terrain, especially where the bedrock appears greenish-black and tough, you may be walking above a nephrite-bearing belt. Even small chips of this material, rounded by water and smoothed over time, can lodge in eddy zones or behind larger stones. Their value comes not from weight, but from translucency, color, consistency, and freedom from fractures. Waterfall systems in these terrains often expose jade not in glittering form, but as dull, waxy cobbles. In the hand, nephrite feels heavier than it looks, slightly oily to the touch, and resists a knife blade with stubborn strength. When broken, its fibers tear rather than snap. These rounded cobbles, mistaken for river rocks by casual walkers, can sell for hundreds if quality is high and size is sufficient for carving or jewelry. Now consider opal, a completely different beast. Born from the slow seep of silica-rich water in volcanic or sedimentary zones, opal doesn't follow gold or diamond logic. It forms in voids, fills fractures, and often appears as veins or nodules in host rock. Where waterfalls cut through rhyolite, basalt, or certain sedimentary bands, they can liberate common or even precious opal fragments. Look for pale, waxy stones with internal play of color or a smooth, porcelain-like surface. When wet, these stones come alive, but only the rare ones flash with full-spectrum hues. Even without the famed color shift, common opal still holds value if clean, well-formed, and large enough for cutting. Field signs include bleached rock zones, honey-colored bands in sedimentary cliffs, or small chunks that fracture conchoidally like broken glass but softer to the touch. In some cases, these float pieces lodge in calm pools below falls, waiting unnoticed among drab river rocks. The wildcard nature of jade and opal lies in how easily they're overlooked. Neither pings on a magnet, neither shows up in black sand traps. They don't gleam in the pan, but their presence can shift the entire narrative of a site, from an empty gravel wash to a potential carving grade or specimen grade find. And unlike placer gold, which depletes, a source-bearing outcrop upstream might yield again and again. The moment a prospector spots a translucent, sharp-edged crystal in their pan, heart rate usually jumps. It's clear it's dense and it resists scratches, surely a diamond. But nature doesn't give up its prizes so easily. One of the most common and convincing imposters in waterfall systems is zircon, a naturally occurring mineral that mimics diamonds in almost every way, except value. Zircon can appear as small, bright grains with brilliant luster. Under a loupe, it shows clean facets and sharp terminations. In wet sediment, it glows like a tiny beacon, reflecting sunlight in silvery white flashes. But its optical charm is deceiving. Many field hunters fall into the trap, assuming any hard, colorless grain with crystal faces must be diamond. In reality, zircons are far more common, especially in stream systems draining granitic, metamorphic, or volcanic terrain. The telltale moment often comes during hardness testing. Diamonds scratch nearly everything: glass, steel, even corundum. Zircons, while hard, don't pass the same benchmark, but field tests are imperfect. A scratch on glass could come from many minerals. That's where thermal conductivity separates truth from hope. A handheld diamond tester, which measures how quickly heat moves through a stone, will register a diamond immediately. Zircon stays cold. That silence on the tester is the crushing confirmation. You found something pretty but not precious. The implications reach further. If zircon is present in large amounts, it often indicates an igneous source zone upstream, but not necessarily one carrying diamonds. This shift reframes the entire logic of the search. What looked like a promising indicator suite must now be reevaluated. Is the chromite actually hematite? Is the garnet almandine rather than pyrope? If the crystal isn't diamond, are the companions still valid? This reversal, while discouraging at first, is also the exact moment the hunt becomes smarter. With false positives out of the way, your toolkit sharpens. You stop chasing shine and start mapping context. A clear crystal is no longer enough. Now you want grain associations, repeatability, and terrain logic. A single zircon means little, but if it appears with spinel, ilmenite, and angular garnet, the odds shift back toward potential. Some of the most valuable discoveries happen just after a misread, because the hunter doubles down on verification. With the diamond illusion shattered, you now know the signals to ignore, and more importantly, the ones that do matter. The mistake becomes the baseline. And that leads directly into a different kind of tracking, one that follows not the water's sparkle but its trail upstream. Where did these minerals start? What changed the flow? And what lies hidden just out of view beneath the path the river no longer takes? Once a stream delivers even a hint of heavy mineral presence, be it gold flakes, garnet, chromite, or a deceptive zircon, the real question emerges: where did it come from? The waterfall may catch, concentrate, or confuse, but it never creates. Everything valuable found below it has a point of origin upstream, often hidden, sometimes displaced. That's where discovery shifts from panning to pursuit. Upstream tracking begins with float, rocks, or mineral fragments washed downstream over time. These pieces aren't random. They form a dispersal pattern, thinning with distance from their source. Careful sampling of gravel bars, plunge zones, and crevice traps moving upstream can reveal a change in concentration. When heavy mineral counts begin to rise or become more angular, you're closing in. Rounded grains suggest travel. Sharp-edged ones hint at proximity. But terrain complicates this. Rivers don't always follow their ancient paths. Paleochannel's old streambeds, now dry or overgrown, often hide the richest clues. These abandoned courses, visible in satellite imagery or exposed after floods, may have once carried the load that current waterfalls now only echo. If indicator minerals increase along a tributary or disappear suddenly along a bend, the source might lie in a former channel now covered by forest, debris, or talus. Rock type is your compass. If heavy indicator minerals are present below a waterfall, walk upstream and note changes in exposed bedrock. A transition from sedimentary to ultramafic rock, or from quartzite to serpentinized peridotite, marks a major shift in geologic potential. Jade-bearing terrain, for instance, often begins where peridotite belts intersect fault lines. Diamond-bearing kimberlite, on the other hand, may reveal itself only through weathered float, crumbly, greenish rock with embedded grains of ilmenite or chromite. Don't ignore debris flows. Landslides and slope collapses upstream of falls often release locked-in mineral zones, scattering them into gullies or feeder creeks. What lands in the plunge pool may be the diluted tail of a concentrated event upstream. Following these scars upslope, especially if they're fresh, can lead directly to pockets of unreleased mineral material. Clues also appear in unnatural patterns. If only one section of the stream shows heavy mineral accumulation while the rest remains barren, suspect a focused source, a vein, a contact zone, or a localized deposit. Documenting pan results at 20-meter intervals upstream can create a gradient map. The point where indicators vanish or spike often aligns with the real deposit. These changes rarely happen gradually. More often, there's a break, a sudden drop or rise in concentration that signals you've crossed a threshold. Once you've narrowed that upstream window, the approach changes. You stop reacting to water and start reading rock. The hammer comes out. You start testing outcrops, checking fracture zones, and looking for surface staining or textural anomalies. The stream brought you here, but the next step is confirming whether what you've found is a remnant or the source itself. Once a promising zone is located, Whether it's below a waterfall, along an inner bend, or up a tributary traced by float, the next move is no longer guesswork. It's method. Grid sampling is how you transform a lucky pan into a documented deposit, how you separate anomaly from pattern, and how any potential value is made real through repeatable results. The first step is to define your area. Even a stretch of 10 meters can hold multiple microzones of concentration depending on flow dynamics, boulder placement, and bedrock texture. Divide this area into a grid, simple squares or zones spaced by equal distances, marked by flagging tape, GPS points, or prominent natural features. Each square becomes its own test site. No skipping, no cherry-picking the best-looking crevice. At each point, take a consistent sample, roughly 1 pan's worth of material from the same depth, usually just above bedrock or from the lowest compacted layer. Remove surface debris first. If moss or roots are present, test them separately. They trap fines differently than gravel does. Wash each sample fully, concentrate it, and document what remains. Photograph it if possible. Label the pan's result: black sand, garnet grains, flakes, or fines. And most importantly, count what shows up, not just what shines. This process often reveals a pattern not visible to the naked eye. One grid line may show little value, until one square lights up with indicator minerals, flakes, or a new type of sediment not seen elsewhere. That pocket becomes a high-priority zone. In past waterfall sites tested this way, prospectors have found that a single bedrock depression, no larger than a dinner plate, held more fines than the rest of the 20-meter stretch combined. Without the grid, that target would have remained buried under randomness. Grid results should be repeatable. If a square yields gold or indicator minerals once, retest it after a light rain or at a different water level. If the pattern holds, it suggests a stable trap. If not, it may have been a one-time flush. This distinction is critical. A site with repeatable yields can be mapped, reported, and if local laws allow, formally worked or even claimed. A one-off is a curiosity. Equally important is what's not found. Absence of indicators in half the grid helps refine the likely path of travel. If garnet and chromite vanish after one bend, you've passed the window. If gold finds fade upstream, you're downstream from the source. This negative data is as useful as a pocket of flakes. It sharpens your focus. For those chasing diamonds, the same grid logic applies, but with a twist. Diamonds may show up in only 1 or 2 cells, surrounded by seemingly barren ground. In this case, follow the indicator suite, not the gem itself. Where garnet, ilmenite, and spinel cluster tightly, you may be sampling a dispersion trail or a contact zone from a degraded kimberlite pipe. At some point in every serious hunt, the question turns from what's here to what's it worth. This is where instinct must yield to logic. Lab tests aren't free. Time spent chasing marginal zones comes at the cost of better ground elsewhere. The decision to assay or to let go rests on a clear, repeatable standard. Is the site producing enough to justify the next level? Assays matter when 2 things are true. First, that you've established a pattern via grid, panning, or dry test that shows repeatable presence of valuable material, not just one-off glints. Second, that the material's type, quantity, and setting suggest commercial, collector, or scientific interest beyond recreational yield. Without both, an assay becomes a curiosity expense. For gold, a typical threshold in remote field testing is consistent fine recovery across multiple pans, ideally with at least a few flakes large enough to weigh. If you're consistently recovering fines that cling to moss or settle in crevices along a defined stretch, and if the pan shows color in at least 30% of test spots, you're into viable territory. If only 1 pan in 10 shows gold and never more than a pinhead, the cost of testing often outweighs the potential return. With diamonds, the logic shifts. A single recovered microdiamond, even a non-gemmy one, can justify a lab submission if it co-occurs with the right indicator minerals. But again, the key is consistency. Labs look for patterns, suites of pyrope garnet, chromite, ilmenite, and spinel that align with known kimberlite dispersion models. Without these, a single clear grain isn't proof, it's noise. The choice to walk away often comes down to context. If you're working a site with decent black sand but no value-bearing grains, no indicator suites, and no upstream rock logic, leave it. Not every waterfall holds treasure. Many simply mimic the traps but lack the feed. No shame in moving on. The best prospectors are those who know when not to dig. If, however, the evidence aligns, repeated finds, consistent heavies, upstream float, and potential host rock, then a small suite of samples is worth sending in. Focus on the best pans, largest flakes, or most indicator-rich residues. Label everything precisely: location, depth, method. Labs respond best to organized data. And consider what you're hoping to confirm. For gold, assays can reveal purity, important if you're in a zone where electrum or silver-rich gold occurs. For diamonds or jade, mineralogical breakdowns can confirm origin and alteration history. Some samples may be more valuable for what they imply about geology than for direct market value. There's also timing. Don't rush to assay early. Wait until your fieldwork has narrowed the site to its richest zones. That one pan in 10 that tested high, try 20 more in that zone, try dry versus wet. Sample after rain, map the gradient. Only when you've wrung the site for consistent clues does it make sense to escalate. Waterfalls are not just beautiful, they're dangerous. The very features that make them ideal mineral traps also make them high-risk environments for anyone working below, above, or alongside them. Steep terrain, loose rock, flash flooding, and legal gray zones can turn a simple prospecting trip into something far more serious. Before you take another step or another sample, you need to know the boundaries, both natural and legal. Start with terrain. Waterfall systems tend to form in areas of high relief, canyons, ravines, or escarpments with slick rock and limited footing. What feels like a sturdy ledge one moment can give way with one misstep. Always approach from downstream if possible, avoiding steep descents or wet moss-covered rock. Wear cleated boots. Bring a second person when testing below vertical drops. The plunge pool area is often undercut. What looks solid may be hollowed beneath by centuries of hydraulic force. Flash flooding is the most underestimated risk. Upstream storms, even ones you can't see or hear, can raise water levels in minutes. A peaceful flow can become a lethal torrent without warning. Always scout upstream conditions, check weather forecasts, and set a physical high water marker when you arrive. If water rises to it, leave immediately. Nightfall compounds this risk. Never prospect under a waterfall after sunset. Wildlife is a quieter threat. Many of the best falls lie in remote or protected zones. Snakes, bears, and territorial animals may share the path or the pool with you. Make noise, carry deterrents if legally allowed, and avoid approaching during early morning or late evening when animal activity peaks. Insect-borne risks like ticks or mosquitoes are real in some waterfall belts, particularly in humid regions with thick vegetation. Then comes legality. Not all waterfalls are fair game. In many regions, especially national or provincial parks, collecting minerals, even for personal use, is prohibited. The line between hobby prospecting and illegal removal can be thin. Always verify land status, public, private, protected, or leased. Contact local land offices if unsure. Even on private land, sampling may require written permission. And if you're documenting anything for potential commercial use, be aware that a casual find can quickly escalate into a regulatory issue. Permits vary by country and jurisdiction. Some allow limited hand tool sampling without claim. Others require a prospector's license even for panning. If you find something valuable and intend to retain or sell it, documentation helps protect you from disputes later. Keep field notes. Mark GPS points. Photograph samples in place before removal. This creates a chain of evidence for origin and ownership. Safety also extends to tools. A pry bar used on slick bedrock, a misstep with a pan in chest-deep water, or even a careless swing of a hammer near a waterfall edge can end a day or worse. Always test footing before stepping. Use lightweight, compact gear. Don't overload packs or strain to lift heavy stones. Injuries in remote zones can mean hours of delay before help arrives. No matter how remote the waterfall or how rugged the terrain, every find eventually faces the same question: what's it worth? The market doesn't care how hard you worked, how deep you hiked, or how beautiful the setting was when you pulled that flake or stone from the gravel. It values clarity, rarity, and proof. And those who understand how value is assessed, from raw gold to rough jade to uncut diamonds, stand the best chance of turning fieldwork into real-world gain. For gold, the calculation is most straightforward. Raw placer gold sells by weight, purity, and form. Fine gold, also called flour gold, commands less per gram than nugget-grade material, largely due to processing costs. Nuggets larger than 1 gram may carry collector premiums, especially if naturally sculpted or from a well-known region. But buyers still test purity. Gold from many waterfall systems averages between 70% to 90% purity. Lower grades may fetch melt value only. High-purity, water-worn nuggets, however, can command 10–20% over spot price on the private market if provenance is documented. Diamonds are a different story entirely. Rough stones found in stream systems must pass multiple hurdles before value is assigned. First, confirmation. It must be a diamond, not zircon or quartz. Then classification, gem grade or industrial. Gem-grade rough with good shape, size, and clarity, especially over 0.5 carats, can be worth hundreds or even thousands per stone depending on color and morphology. Industrial-grade stones, which make up the vast majority of rough diamonds, may fetch far less, often pennies on the carat, unless sold in bulk. But with diamonds, origin matters. Stones from recognized fields with proper chain of custody, legally obtained, ethically sourced, move easily into legitimate markets. Stones without provenance, even if genuine, may be rejected by buyers, labs, or dealers unwilling to risk association with conflict sources or illegal trade. That's why early documentation and field records matter. A legitimate find, properly mapped and tested, opens doors. An undocumented rock in a pocket invites suspicion. Jade and opal sit between the two. Their value is highly variable, driven not just by mineral quality, but by aesthetics, size, and cutting potential. Nephrite jade found in serpentinized zones below waterfalls can sell from $20 to $200 per kilo for carving-grade material. Rare translucent green nephrite, especially with uniform color and minimal fractures, can spike into the thousands. Opal's value depends entirely on type. Common opal, even clean and attractive, may bring $5.50 per piece. Precious opal with strong play of color, even in small nodules, can leap to hundreds if cuttable. Again, visual appeal and crack-free structure dominate pricing logic. One consistent theme emerges across all materials. Buyers need confidence. That means clean samples, well-documented location data, and increasingly third-party verification. Even rough, uncut material sells better when accompanied by basic field context. Photos in situ, sample logs, density tests, even video of collection. Online marketplaces for raw minerals now demand this level of transparency. Serious buyers, collectors, and lapidaries avoid unverified field finds. Finally, remember the tiers. Local gem shows may yield fast cash for small finds but lower prices. Direct sales to lapidary artists or small workshops may bring better returns with some negotiation. Auction houses and mineral expos cater to higher-end specimens, but only for material that's rare, clean, and convincingly sourced. In the world of field discoveries, not every mistake is innocent, and not every buyer is honest. The same traits that make gold, jade, and diamonds valuable also make them targets for imitation. Even in remote waterfall systems, fraud isn't just a market problem. It starts at the source, when identification slips or when someone sees profit in deception. Knowing the difference between a genuine misread and an intentional fake can protect both your find and your credibility. Start with the simplest trap, misidentification. It's common even among experienced hobbyists to confuse high-luster minerals with precious ones. Mica and biotite mimic fine gold. Zircon, quartz, or topaz often get mistaken for diamonds. Hematite masquerades as chromite. In the rush of discovery, even a trained eye can get it wrong without proper tests. That's why field tools, magnet, loop, scratch kit, and conductivity tester aren't optional. They're your first line of defense. Then come the built fakes. These range from obvious scams, like dyed quartz sold as jade, to highly convincing lab-made stones passed off as natural. Synthetic diamonds, for instance, are nearly indistinguishable from natural ones without specialized equipment. On the open market, unscrupulous sellers may take industrial synthetics, tumble them for a more natural look, and offer them as rough river finds. If your waterfall harvested diamond looks too clean, too clear, or oddly shaped, ask harder questions. Glass is another common imposter. High-lead glass fragments, especially those shaped by water, can resemble everything from sapphire to peridot. These pieces often show tiny bubbles inside, one of the few reliable visual giveaways. Under a loupe, they may reveal curved flow lines or chipped corners that fracture too easily for any real gem. With gold, the fraud flips direction. Instead of inflating value, fakes often try to cheapen the real thing. Buyers may claim a nugget is too low in purity or accuse a seller of mixing in brass or pyrite. In cases like this, a simple acid test or electronic gold tester can end the debate, but only if you've prepared in advance. Keep records. Photograph your finds next to landmarks or collection markers. A nugget without context is vulnerable. A nugget with a paper trail resists being lowballed. Even documentation can be falsified. In competitive zones where jade or opal is found, some dealers forge origin claims to align with famous regions. Australian opal fetches more than Peruvian. British Columbian jade sells higher than lesser-known sources. If you plan to sell, ensure your own records are watertight. If you plan to buy, ask for proof, photos, assays, field logs. A seller who resists those questions is waving a red flag. But perhaps the most insidious error is self-deception. The belief that a shiny stone must be valuable simply because it was hard to find. The more time invested, the more likely the mind wants to believe it paid off. That's when you ignore weak test results or downplay inconsistencies. Every serious prospector makes this mistake at least once. The cure is verification, field tests, repeatable panning outside opinions, lab confirmation when needed, and always a willingness to be wrong so that when you're finally right, the truth is unshakable. At the end of a serious field investigation, when the pans are washed, the concentrates sorted and the samples logged, the final step is confirmation. The test suite. This is the moment where every assumption is put to trial, where field observations meet physical proof, and where the results either hold or fall apart under comparison. It's not dramatic, but it's definitive. Start with the samples. Select a cross-section of your best concentrates, the richest pan from below the waterfall, a few from the grid sampling zone, and any unique finds, clear crystals, unusual stones, heavy grains. Each one should be tested using the same baseline suite. Magnet response, visual inspection under loop, streak test, density feel, and if available, thermal conductivity for suspected diamonds and electrical conductivity for metals. The black sand sample responds first. A neodymium magnet quickly confirms heavy magnetite content, no surprise. Ilmenite, though magnetic, shows slightly less pull and may separate out with more precise positioning. Once magnetic material is removed, what's left tells the real story. Visible garnet grains, deep red, semi-translucent, chromite nodules, matte black, inert to magnet, and a few light-colored, sharp-edged grains. These clear grains draw attention. Under loop they appear angular, high luster, but the thermal probe is silent, no conductivity, suspected diamond, no zircon. Scratch test confirms moderate hardness but not enough. You mark them as non-diamond indicators, still useful for tracing but not the prize. The gold test sample tells a different tale. 3 pans from the grid zone yield consistent fine flakes, each adhering stubbornly to the pan edge during cleanup. Under pressure they smear rather than crack. They float briefly, then sink. A conductivity pen chirps, confirming metallic presence. 1 flake is large enough for a scale reading, 0.13 grams, modest but real. Repeatable pans hold 2 flakes each. The verdict, fine placer gold, likely sourced nearby. Then comes the jade sample, a rounded waxy cobble with green-gray tones taken from a waterfall base. Knife blade glances off its surface. Loop reveals fibrous texture, no sparkle, no fracture lines. Weight in hand confirms density slightly above average. You test a small chip, still tough, not glass, not serpentine, high chance of nephrite. Assay will confirm, but all field signals say go. The opal-like nodule shows mixed traits. Smooth, porcelain texture, no play of color but consistent body tone. It fractures conchoidally like glass but without air bubbles or curved flow lines. When wet it glows slightly, revealing internal uniformity. Likely common opal. Value will depend on clarity and cutting potential. A specimen, not a gem, but real. Across all tests, the theme is confirmation through comparison. The magnet test isolates the iron-rich components. The loop reveals structure. Density and scratch separate imposters from contenders, and conductivity, the final check, closes the door on guesswork. If the stone talks, it's real. If it stays silent, it's not what it claims. No single test tells the full story, but together this suite creates a profile. It validates what the pan suggested, what the terrain hinted at, and what the grid confirmed. The work becomes more than just field notes. It becomes evidence.